that can very slowly. And so what we show is that by taking advantage of the structure of the variational family through score matching, we get simple solutions that allow us to sidestep gradient-based optimization. And in many cases, we are actually going to get faster convergence. So this is joint work with my collaborators, Chirag, Lucas, Charles, Robert, David, and Lawrence. Right, so probabilistic inference is used widely in the sciences and in many other fields. And so I have many collaborators that are interested in using these tools in applications such as parameter estimation in astrophysics, estimating biophysical properties of proteins, predicting stable materials, and optimizing spatial genomics studies. So these are problems where we rely heavily on probabilistic models and would like to be able to quickly iterate through a number of different modeling choices without having to think about redoing our inference every time. And so the goal is to really think about black box inference methods. So these are methods where there are no model-specific derivations, and so they become easily applicable to a wide class of models. In particular, in the world of variational inference, black box VI based on stochastic gradient descent can often converge very slowly due to things like noisy gradients, sensitivity to learning rates, and other hyperparameters. And there's just a number of optimization challenges when using richer variational families. For instance, you can often get better performance using a diagonal Gaussian variational approximation than using one with a full covariance due to the difficulty of this optimization problem. So in today's talk, I'm going to talk about score-based black box VI. So this is a new way of doing BBVI by comparing the scores of Q, our variational distribution, and P, our target. In particular, I'll talk about batch and match, or BAM. This is a iterative algorithm that fits a full covariance Gaussian, and we're going to observe fast convergence relative to these stochastic gradient-based algorithms. I'll also talk about EigenVI. So this is a method where we propose using what we call is the orthonormal variational family. So this is a family that's flexible, yet also tractable. And in particular, these approaches will not rely on gradient-based optimization. Okay, so in variational inference, the goal is to try to approximate this target distribution over latent variables, P of Z. So this is a target distribution where we assume we can't sample from it or evaluate it. For instance, it might have the following form where it's equal to some rho of Z divided by some intractable normalizing constant. So this is common in Bayesian inference, for instance, where rho might represent your joint distribution. So in variational inference, what we do is the basic idea is we choose a tractable family of distributions Q, for instance, a Gaussian with diagonal covariance. And then the goal is to then find the member of this family that is closest to our target distribution P in some divergence. And so what is most commonly used is the Kolbach-Leibler divergence, and in particular, this reverse KL divergence. And so once we minimize that in some way, then we approximate our target distribution with this optimal distribution. So in classical VI, typically you would use some kind of gradient-based optimization of the KL, or equivalently the evidence lower bound, or ELBO. And you might use something like coordinate ascent, and this process would involve a lot of assumptions on the target distribution, and in particular, a lot of many model-specific derivations were needed here. And so this made variational inference perhaps not the most accessible for practitioners that would like to apply this method. In more recent years, there's been kind of a transition to developing more black box variational inference methods. So here we're not making model-specific derivations. We just sort of assume that we can write down this log unnormalized target distribution, for instance, our log joint distribution. And In this talk in particular, we assume that this log unnormalized target is differentiable. So what we assume is we can compute this score given by the gradient of log P of Z. In particular, thanks to advances in automatic differentiation, black box variational inference methods are now readily applied in a number of probabilistic programming software, making it very accessible to practitioners. So here, all you have to do is write down some log joint distribution, and then the software will then run this inference algorithm for you. So in these stochastic gradient-based black box variational inference algorithms, here we're going to focus on one particular instance of this, which is called automatic differentiation VI or ADVI. And this uses what's called a reparameterization gradient, but there's other forms of BBVI as well. But the sort of idea is that this is kind of a very general approach, and that it's not really making very good use of specific knowledge about the variational family itself. Perhaps if you're using this reparameterization approach, you need to require that it is a family that can support reparameterization, but otherwise we're just doing gradient descent. And this can be very slow to converge due to these noisy gradients and sensitivity to our learning parameters. And this convergence often worsens with richer variational families, such as, for instance, what I mentioned earlier, the full covariance Gaussian family. So the idea is what if we were to use additional information about the variational family itself? For instance, the scores of the variational family. And so, why do we want to do score matching? So suppose, for instance, our target were actually Gaussian. Then the score function for both the target and the variational distribution is just a quadratic. And so you can imagine trying to look at samples in your latent space and trying to match the scores at those points. And in particular, this is something that you can do in kind of order on the number of samples you need to exactly recover the mean and covariance is on the order of the dimension of the problem. However, we'd like to do this process for non-Gaussian targets. And so again, this is really nice for this black box procedure because we don't actually need access to the target itself. We just need its score. And so this idea of score matching has been explored in prior work, which was trying to match the scores exactly. And so this is something that works well for Gaussians, but basically, when you're working with non-Gaussian targets, additional heuristics were needed. And so the idea is we'd like to kind of relax this using a divergence. And so can we develop some kind of score-based divergence to do black box variational inference? So concretely, we're going to consider a variational family Q that is a full covariance Gaussian. And we're going to define the following divergence. So this measures the agreement between the scores of Q and P. And it's going to be given by the following. So this divergence is the expectation with respect to Q of the difference between the scores of Q and the scores of P. And here I have this covariance weighting. So what this notation means is that we're going to weight what's inside the norm by the covariance of Q. So this divergence has a number of properties. One, it's non-negative with equality if and only if P equals Q, and it's invariant to affine transformations. And so these are properties you would like a divergence to have. They're satisfied by things such as the KL divergence, for instance. But one kind of interesting property of this second point is that it's actually going to lead to closed form solutions for doing Gaussian score-based BBVI. In particular, without this covariance weighting here, we get something what's called the Fisher divergence, and you don't get these nice closed form solutions in that case. So how do we use this to do score-based variational inference? So conceptually, what we'd like is to find the member of our variational family that minimizes this score-based divergence. And so one thing you can do is try to estimate the score divergence using samples. In particular, Here is what, a version of this using Monte Carlo estimate would look like. The problem is that we can't simultaneously sample from and optimize over Q. And so we need to decouple this distribution from, the optimization problem. And so what we're going to do is propose an iterative procedure where we are kind of constructing this sequence of variational approximations where at the tth step, we'll go to the next step by minimizing some empirical divergence with respect to QT itself here. So this is the current variational distribution. And so what this is going to do is introduce some bias into this estimate because we're now sampling from QT instead of Q. And in order to sort of handle this, we want to then add some kind of regularization to our score-based objective to ensure that we don't move too far from QT. And so what we're going to do is propose what's called a proximal point algorithm. And so the actual algorithm looks like the following. So this is what we call batch and match, and it iterates between a batch step and a match step. So in the batch step, what we do is, given the current variational estimate, QT, we're going to sample a batch of points where B is the batch size. And then we can compute our score-based divergence on this batch of points. Then we'll run the match step where we fit this new variational distribution QT plus 1, where the objective here is the score-based divergence we're computing in the previous step, plus some KL regularizer between QT and Q. And note that because these are Gaussian, we have this in closed form, the second term. And then finally here, lambda t represents some learning rate. So the idea is that when lambda t is small, this regularization becomes large. And so it encourages these two, this QT plus 1 to remain close to QT. So since we're working with Gaussians, we can actually solve the match step in closed form. In particular, we'll have an update for our covariance and for our mean. And so for the covariance update, it arises from solving a quadratic matrix equation. The exact update is in our paper, but it basically looks something like the following, where here UT and VT are matrices that depend on the current covariance and statistics of the batch of samples, Z1 through ZB, and their scores. Then there's this nice mean update that looks like the following, where here G bar represents the mean of scores computed on our batch of samples. And in particular, this depends on the covariance update. And so we need to perform the update in this order. Oops. So finally, so if we do this, the covariance update naively, the computational cost would be cubic. But if the batch size is smaller than dimension, then we can actually perform a low rank update that becomes quadratic in the dimension. Okay, so this is the algorithm. And what can we say about it? So in particular, one thing we show is that if the target itself is Gaussian and we take the batch size to infinity, then for any learning rate, lambda t, this mean and covariance update converges exponentially quickly to the target mean and covariance. And in particular, if you there's only recently theory that's been developed for this sort of stochastic gradient-based approach. And even with Gaussian targets, this requires a very particular tuning of the learning rate. In addition, while our results here are in the infinite batch limit, we observe empirically for finite batch sizes that we get rapid convergence when the target is Gaussian. And so here, each panel represents some increasing number of dimensions of a Gaussian, and then these dark purple curves represent batch and match, where the label represents the batch size. So here we're using fairly small batch sizes, and we're still getting, I'd say, very fast convergence. And you can sort of see in contrast how slowly this full covariance ADVI method is converging here. Okay, so what happens though for non-Gaussian targets? This is something that we look at empirically in a number of examples. So first, we looked at some hierarchical Bayesian models. So these are problems that are known to be unimodal, but they're not going to be exactly Gaussian. And so we compare to ADVI again, as well as this sort of Gaussian score matching method that's trying to do exact score matching. And so both of these depend on a batch size of B. And what we measure here on the y-axis is the relative mean error. So this tells us how good is this variational estimate of the mean relative to the MCMC estimate of the mean. In particular, here are 3 problems we looked at, and in all of these, the dashed line is the smaller batch size of 8, and the solid line represents the larger batch size of 32. And on the x-axis, we're showing the number of gradient evaluations. So the main takeaway here is that sort of unlike the other methods, BAM tends to be better at utilizing these larger batch sizes to converge faster. And this is also nice because it suggests that BAM may benefit more from parallelization across the batch in each iteration. So the second sort of problem we looked at was a higher dimensional application in deep generative modeling. So here we have the data set consisting of images, and the image is, a bunch of pixels. And so we're going to come up with a model that is a lower dimensional latent representation, Zn, of this image. So here our latent representation is in 256 dimensions. And so we have the following deep generative model where we draw our latent variable Zn from a Gaussian, and we assume that the image, given this latent variable, is generated from a Gaussian, where here our likelihood is parameterized by the output of a neural network. And these parameters, theta hat, are the parameters of our neural network. They've been pre-trained to maximize marginal likelihood objective. So the problem is now, given a new image, we'd like to approximate P of Z prime given X prime using variational inference. And so what we do is we reconstruct X prime by feeding the posterior mean estimate that we get out of VI into our neural network. And here I'm showing these image reconstructions for the 3 methods, where this x-axis represents iterations. And they're all using the same batch size here. And so you can see from the image reconstruction that this BAM method is converging much faster. But we also measured the mean squared error to measure this reconstruction error. And so here what we see is that for each panel represents different batch size. And so for the smaller batch sizes, we found that BAM tended to not be very stable. But once you kind of increase the batch size, we find that it's actually doing much better. And in fact, BAM with this largest batch size converges with ADVI using any setting of batch size. And so this again sort of suggests how this might also benefit from parallelization. Okay, so now there's a number of extensions of BAM we could consider. So here we might think about, what if we wanted to go to even larger dimensions? So far in the previous setting, we were sort of assuming we could fit this full covariance with O of D squared parameters, where D is a dimension. If we were wanting to work with much higher dimensional problems, one thing we considered was projecting the covariance update to something with low rank plus diagonal structure. And so this is something we can do using an EM algorithm, and we get a new covariance update that now has O of D cost. Another question you might have is, how can we use BAM with large scale data sets? So here now you might have many, many data points where suddenly evaluating these scores becomes very expensive. So in future work, we're looking at using BAM, where you would instead pass in a noisy score that is computed from a subsample data set. Finally, you might be wondering about non-Gaussian variational families. So this is going to take us to the sort of next part, where I'll talk about EigenVI. So here, what we're going to do is consider a flexible but tractable variational family. So this is going to be constructed from orthogonal function expansions, and these are inspired by wave functions in quantum mechanics. And what we'll see is that when we minimize a score-based divergence, this also yields a nice closed-form solution. And it's in the form of a minimum eigenvalue problem. Okay, so what is this kind of new variational family that we're talking about? So we call this the orthonormal variational family, and we'll construct it by starting from a complete orthonormal basis set, phi of k. So here, these phi's satisfy the following property, where if you integrate over them, they're 1 if k equals k prime and 0 otherwise. And the variational distribution will take the following form. So here we're going to think about basically taking a linear combination of this basis, where here the alphas represent these coefficients are our variational parameters now. And then once we take this linear combination, we'll square it. And so the squaring ensures that Q of z is non-negative. And in particular, we'll also enforce this constraint that the sum of the squares of these coefficients is equal to 1. And so this ensures that Q is normalized. So, this is kind of nice because we would like this to be a normalized distribution. In addition, basically this property of orthogonality of our basis set allows us to do a lot of integration efficiently. And so one of the things that we get out of this is that we can actually sample from Q efficiently because we can compute marginals efficiently. We can also compute low order moments, such as, say, the mean or variance of this family in closed form. So what are some examples of orthonormal families? So you could consider ones constructed from, say, Legendre polynomials. So these are used over a bounded interval. So here I'm plotting this on -1 to 1. And so k represents the order of the expansion. So how many of these basis functions are we going to use? And so the target distribution here is given by this black dashed line. When k equals 1, we get this uniform distribution. So this is what's also called the base distribution. And as we increase the order, you can see that this family becomes more and more flexible. You can also consider other basis sets, such as ones given by Fourier series or Hermite polynomials. The latter is especially nice because the base distribution itself is Gaussian. This is used for modeling things over the real line. And so you can kind of view this as a systematic way of incorporating non-Gaussianity through these higher order expansions. So far, I'm just showing these one-dimensional pictures, but in higher dimensions, we can actually use Cartesian products. So for example, in 2 dimensions, the variational distribution looks something like the following, where we now have the sum over k1 and k2 terms, alpha jk times phi j z1, phi k z2, and then the whole thing squared. And of course, one thing to note here is that in d dimensions, we now have this product of kd basis functions. And so this can very quickly get expensive if we want to use multiple basis functions per dimension. So that's something we have to be mindful throughout this whole process. So why is this method called EigenVI? So essentially, the summary is that when we do score matching, we're solving an eigenvalue problem. In particular, the form of score matching that we're going to consider is minimizing an important sampled estimate of the Fisher divergence on a batch of B samples. So the estimate takes the following form, where here pi represents a proposal distribution, And then this term in the norm is the difference between the scores of our variational distribution Q and our target P. So in particular, when we go to do this optimization and we minimize this estimate over some order K orthonormal variational family, it turns out that this takes this quadratic form where M is a matrix that is a function of the scores and then gradients and evaluations of these basis functions, the phi's from earlier. And so it turns out that minimizing this score-based divergence here is equivalent to minimizing, finding the minimum eigenvalue of this matrix M. And so here, to do variational inference, we're now solving an eigenvalue problem instead of doing gradient-based optimization. And also note that this matrix M can be constructed in parallel over all of our samples, unlike in iterative methods. And so there are some potential advantages there. Okay, so in the next part, I'm going to focus on this setting of doing EigenVI and RD. So in RD, recall we want to use this Hermite family, or we're going to assume that we're using this Hermite family. And if you recall, the lowest order expansion here is a standard normal. Again, we have this issue that in D dimensions, this becomes very kind of expensive quickly. So the idea is that we would like to reduce the number of basis functions needed by making our target distribution closer to our base distribution or this standard normal distribution. So the intuition can be seen by a couple of 1D examples where first here I'm showing a Gaussian target where the mean is now kind of at 3 and the variance has been shrunken away from a standard normal. So you can see what the standard normal is by this order 1 expansion here. And so the idea is if we could somehow standardize this black curve, then we could actually fit this with just the lowest order expansion alone. Without the standardization, we need about 16 basis functions to get a closer fit. Now we'll look at a non-Gaussian target. So this is the one that I had earlier with the Hermite family, where we have this mixture of Gaussians, and you can see that here these the larger modes are, they're close to the origin or the space distribution. But what happens is when we translate this mixture where these largest modes are now away from the origin, we see that we actually need about twice as many basis functions to fit this target distribution. So, concretely, the idea is that, if we standardize our target and then we fit EigenVI in the transform space, we will hopefully be able to use kind of a low order EigenVI expansion to then fit this target distribution. So our approach is to fit a Gaussian to our target distribution, and then we'll standardize the input using some mean and covariance. So these are going to be some estimate of the mean and covariance of our target. And in particular, we'll construct this transformation by using batch and match to fit a Gaussian. But you could use your favorite method to actually get estimates of mu and sigma and still perform this process. So conceptually, what we'd like to do is transform our target by standardizing. So this makes our target sort of more isotropic, and then do a low order EigenVI fit in the transform space. And then we can undo this change of variables and get back the approximation to our target distribution. The nice thing about the standardization also is that it kind of leads to a number of natural proposal distributions for pi, because now our target is now centered, and so this suggests using distributions that are centered with heavy enough tails. Okay, so all right, so here are some examples of EigenVI in RD. Um, so in particular, we're going to look at some two-dimensional non-Gaussian targets. And in each row, I have a different target distribution. So for instance, this is a mixture of Gaussians. And you can see that in the second panel, this is sort of what happens when we fit a Gaussian. And I believe this is the output of actually just the batch and batch algorithm here. Um, and then you can kind of compare the next three columns, what we get from using EigenVI with an increasing number of basis functions. So here we can see that we don't get a very good fit when we're using 2 in each dimension. But as we increase this number, we get a better and better fit. And I'll kind of add that I did not standardize in this problem, so that's something that might help here in terms of reducing the number of basis functions. And then, of course, just a couple more examples. Here's a cross distribution where we're then fitting this EigenVI family with more and more basis functions. And then the final row, we show a funnel distribution. So this type of structure is common in hierarchical Bayesian models. And so here you can see that, again, as we increase the number of basis functions, we're getting a better fit. In particular, we also looked at some real data examples using hierarchical models. And I'll just show one here. So this is this 8 schools hierarchical model. It's a 10-dimensional problem, and it has some non-Gaussianity in the tails. So I'll show the posterior marginals that we get out of the even dimensional coordinates. Okay, so first, we'll look at what happens when we fit batch and match VI. So this is fitting a Gaussian. And in each of these plots, we're showing in the green histograms, the VI fits. And then these dark gray histograms represent samples from Hamiltonian Monte Carlo. And so you can see that when you fit the Gaussian, it's not able to fit this tail here. And then sort of qualitatively, we compare to a normalizing flow. So this is using a neural network-based variational family and doing this elbow optimization. And so this is a very flexible family that is able to fit the tails. And we see that, EigenVI with standardization is able to perform competitively to a flow in this example. But I think in the version of the normalizing flow, there's many more parameters that we found the optimization to be sensitive to, whereas the parameters of EigenVI are sort of, what is the order of the family and how many, samples do we want to take? Okay, so I guess I'll summarize kind of the main points of the talk. So we discussed variational inference algorithms that minimize score-based divergences. So the sort of important thing is they're black box and that they only require computing the score of the target. And we talked about 2 algorithms. One is this batch and match algorithm. So this is fitting a full covariance Gaussian. And we show that, with this proximal point subproblem, we're able to get closed form updates. And for EigenVI, this is another score-based method where we're using this orthonormal variational family and doing minimizing the score-based objective is equivalent to minimizing finding the minimum eigenvalue of some matrix. And we have some code available for our methods online on GitHub, in JAX and Julia. So there's many future directions. So I think for the BAM convergence, there's more theoretical analyses that we would like to do for finite batches and non-Gaussian families. And then there's just a number of methodological extensions for both of these methods, but for EigenVI especially, we like to develop something that works in higher dimensional spaces, because most of the problems we are looking at are limited to lower dimensional spaces. But you can also imagine looking at other types of orthonormal families on bounded spaces using different basis sets. And then, of course, another direction is testing these methods on massive data sets and seeing if, how well they perform in those cases. Okay, so I have a number of references here that if you're interested, you can check out for more details. The first is on batch and match, and the second one is on EigenVI. And then the final one is this kind of extension I described earlier, where we're basically projecting the covariance update to something with low rank plus diagonal structure. All right, well, thanks for listening. And if there are any questions, I'd be really happy to discuss further.
Thank you for the nice talk. I'll stop the recording now.